So going back to the basics of solving a little system of two equations in two unknowns, let's just look at how the traditional method of solving it works. So we have these two equations, and what we can do is try and get rid of this 4 so that the last equation only has one of the variables in, so it only has x2 in it. So I can do that by subtracting twice equation 1. So that I get 4x1 and subtract it, leaving 0x1. And then, of course, what that does here is subtract 6x2 from that, giving us minus 5x2. At this point, we've more or less got the answer, because minus 5x2 is minus 3, gives us x2. And then if we've got x2 and we put it in there, then it's easy to get x1. So x2 is 3 over 5. Just notice the minus on both sides. And then, given we've got x2, we can find 2x1 is 2 take away 3 times x2, which is 3 over 5, which is just a fifth. So x1 is a half that, and x1 is a tenth. And of course, we should put it back in and do our fractions calculation here to check that this works. Okay, so we can writing it as a matrix. How does that work? We're subtracting row 1 from row 2, like this. And there's nothing really that different. It's just written in matrix notation. So we use the transformation involving subtracting multiples of rows above from the row that we're looking at to get rid of a variable. In the end, the aim of the first step is to get a system of equations that looks like this. Let's just look at this. These x1 and x2 have disappeared here. x1 has disappeared, making it triangular. And at this point, we can see we know x3 because it only appears as only one variable in this last equation. When we know x3, we put it in here, so we know x2. And finally, we know x2 and x3, so we know x1, substituting back in as we go up. So if we can reduce it to this triangular form, then we can solve it. Well, provided the diagonals are not 0, of course, and of course something has to possibly go wrong in some situations because the matrix might be singular. But putting the back substitution in explicitly, x3 is b3 over a33, and you can just see that you're going to divide by these diagonals on the matrix. Of course, we'd have got to this by doing some operations, so this wasn't the original matrix. Okay, and you see this will work as long as none of the diagonals are 0. Okay, as a matrix, we call a matrix like this upper triangular, and it means that below the main diagonal we have zeros, upper triangular. So that's the main diagonal, and this is upper triangular. So if we can get to upper triangular, we're pretty much sorted. So here's an example of doing back substitution. Suppose we've got the upper triangular matrix, like this. Then well, we know x3 is 2. I suppose in a way we've just divided the bottom row by 5 to get that. So you could write it like this with a 1, and of course if we have 1s there, then we can read off the answer, x3 equals 2. But an even nicer thing about having a 1 here is it makes it easy to get rid of this number. So we can take the third row, away from the second row and get rid of this 1. And of course, if it wasn't a 1, we'd have to multiply it by something. And I've changed the row, I've changed the right hand side as well, using the same operation. In other words, we've subtracted the row 3 from row 2. So now we've got this row reads x2 equals 1, and so we now know x2 as well. And so the thing that's emerging from this is once we've got lower triangular, we can go back up using subtracting multiples of each row from the row above, and getting rid of these numbers that are off the diagonal. And when we've only got diagonal numbers, we can just read off the answer. So we now get rid of that 3 by taking 3 of using row 3 to get rid of that number 3. So we take 3 of that away. And then finally, we use this row to get rid of that number. And now we've got a diagonal matrix, and we can just read off the answer. This is actually the answer. So we started with a lower triangular matrix, and we got rid of the upper triangle by first making that number 1, and then using that to get rid of those numbers. We make this one 1 and use it to get rid of that number. If you like, you can also divide this row, but if there's a number here that's not 1, so now we can just read off the answer. So that's the solution. So that's back substitution, and in general the back substitution solution can be written down. Of course it looks a bit complicated to write down. It's actually quite easy to do, but the nth component, the xn, is just bn over ann, and then to get the next component, the back substitution is bn minus an minus 1 n xn, that's the previous row. And in general you have to subtract all the solutions you've already found multiplied by the coefficient, which just corresponds to moving the things you've already found in each equation over to the other side. And it works as long as the diagonals are not 0. Okay, so in the next segment we're going to formalize this more as Gaussian elimination.